Okay, so we have seen how certain contour integrals of certain integrands may be independent of the path, right? And uh, when this is true, it's useful to introduce the notion of an antiderivative, right? So that's the subject matter for this lecture. Okay, so when we say that a certain contour integral is independent of the path, so what it effectively means is that at every point, when you're suppose you have an integral of some function f of z that you're thinking of, there is a function capital F of z that you can introduce such that the derivative of this function capital F at that point is equal to f of z, right? So if you're able to find a function capital F of z such that whose derivative at any point in your domain of interest is equal to f of z, small f of z, then you call this capital F of z as an antiderivative, right? And of course, this capital F of z is I mean it's unique, but only up to a constant, because if f capital F prime of z is equal to small f of z, then it also means that you can, if you add some arbitrary constant to your capital F of z, then that also is going to be a valid antiderivative, right? So it turns out that if f of z is continuous, and then if you are able to find an antiderivative which is defined throughout d, right, by definition, the fact that this capital F prime of z is this continuous function f of z, it automatically implies that capital F of z is analytic in the whole region. And so just the continuity of f of z in this domain and the existence of an antiderivative is completely equivalent to any of these three ways of looking at it, right? So if it so happens that a function f of z has an antiderivative capital F of z throughout a domain D, that's the same thing as saying that integrals of f of z along contours which all lie entirely in this domain D, and whichever integral you do, right, starting from some point z1 to z2, no matter which path you take, as long as the entire path lies inside this domain, it's all going to have the same value, and that value is going to be simply given by the value of this capital F function at the final point minus the value of this antiderivative at the initial point, right? So this is a bit like how we think of definite integrals of real variables, right? So the statement here is that this independence, the path independence of contour integrals in some domain is completely equivalent to the existence of an antiderivative. So every point f of z, every point z, so you have a small f of z defined, and there is a well-defined capital F of z for every point inside your domain, right, whose derivative at that point will give you small f of z. And it's also equivalent to saying that all integrals of f of z around closed contours such that the contour lies entirely in your domain must necessarily be 0, right? So this also is clear in the sense that if a property 2 holds, then if z2, if you're going around some path of whatever the path is, and then you return to where you started, then it's going to be capital F of z, z naught, if you wish, where you started, minus capital F of z naught, so it is going to be 0. So if this holds for every path in your domain, the statement is that 3 is the same as 2, and 2 is the same as 1, and 1 is the same as 3. So any of these three statements automatically implies every other statement, right? So we will not go into proving these statements, but it is true, and it's sort of intuitively clear that they're all really talking about the same thing. And then we will see some consequences of this. Let's look at a few examples where we try and apply this idea of an antiderivative. So this function f of z is equal to z. We have already looked at this function f of z is equal to z, and it has an antiderivative, and it is clear that this antiderivative is z squared by 2 up to an arbitrary constant. So z squared by 2, because if you take the derivative of z squared by 2, you're going to get z, right, throughout the plane. And therefore, if you want to take the derivative from some initial point to some final point, you just need to specify initial point and final point. If you're taking a contour integral of this kind, it simply does not matter which path you're going to take. And so the answer is simply given by z squared by 2, final point minus initial point. So it's just 1 plus I the whole squared over 2 minus 0. That's going to be 1 plus 2i plus I squared. That 1 and my I squared will cancel, so then you're left with just I. Right? But this is a contour integral. This is a result which we are familiar with, because we worked out the same type of a contour integral, evaluating it over 3 different paths. We first looked at path which went along the x-axis and then perpendicular, and then we looked at one which went along the y direction and then turned to the right, and then we also looked at a path where it went along a straight line. So it simply does not matter which path you take, because this function f of z is analytic in this entire, it's an entire function, right? So in the entire complex plane, it's going to be analytic. So, well, I mean, in this case, as far as this theorem that we are using is concerned, we are not even really talking about analyticity of f of z, right? It's simply, all that is required is continuity, right, which is a weaker condition. But the point is that there is a well-defined notion of an antiderivative, and you go through this entire path. So it's only your final answer, your answer for a contour integral will depend only on the final point and the initial point, and not on the path. So let's look at another example where this is true. So suppose you take the function f of z is equal to 1 over z squared. Right, so 1 over z squared is continuous everywhere except at the origin, and this has an antiderivative for all mod z greater than 0. Right, so we can verify that minus 1 over z, right, it's analytic everywhere except at z equal to 0. So if you take its derivative, it's going to be 1 over z squared. And so if you take any closed contour that does not include the origin, right, it should not cross the origin, it can go around the origin. So for this function, you're going to get 1 over z squared for any closed contour dz, it's going to be 0. Right, so we have already verified okay, so so this is actually something that we are yet to directly verify, but we will do so by some alternate techniques, right? So one way is to actually consider a circular path and then work this out. But what we have just said is, so in this result we have looked at it from a from the point of view of this theorem, which we have not proved, but we have sort of intuitively accepted. And so as a consequence of that, we have seen that this contour integral of 1 over z squared dz over any contour c which goes around the origin is going to be 0. Right? So instead of saying we have already directly verified, I will say we can directly verify. Right? So because I don't think we have done it yet, but it is something we will look at again. So but also it could be part of your homework. We can directly verify the above result for contour C that are circular paths. Right, so what you have to do is just consider a circular path of radius r, then write down C as e to the r times e to the I theta, and then work out this contour integral, and then you can show it for circular paths that this result holds. But here we have just written down a more general result, and that is that this closed contour integral is 0 no matter what the shape of this contour C is. Let's look at one more example which looks very similar to this, but where we have to be more careful. Right? Suppose we consider the function f of z is equal to 1 over z. Right? So now this function is also continuous everywhere except at the origin. But you cannot blindly conclude that this similar type of a contour integral for the function 1 over z dz is going to be 0. In fact, it is not going to be 0. The reason is the antiderivative of this function 1 over z is log z, which is a multivalued function. Although this function f of z itself is not multivalued, so there is no problem with this function as long as you are not at z equal to 0. But Log of z is a multi-valued function, and so when you're traversing a closed path, you're going to necessarily cross the branch cut, and that's not allowed, right? So if it is not even defined at the point, that you're crossing, then it's definitely not differentiable. So if we consider a contour of radius r centered around the origin like this, so there is no way to complete this path without ever crossing a branch cut, right? So you cannot blindly apply this result. But what there is a trick one can do, which is to say, if I want this entire path, then I can break it up into a contour C1, which goes from minus Ri to plus Ri along C1, and then you come back around C2, right? So always going in anti-clockwise direction. So in fact, this contour integral over C 1 over z dz is the same as contour integral over C1 1 over c dz plus contour integral C2 1 over z dz. And we can work out these two integrals separately, but using two branch cuts as far as the log function is concerned. The first one is the easier one because we can directly use the principal branch. So suppose I look at I1 is equal to integral c over c1 1 over z dz, and we work in the principal branch. Then I take log z to be log r plus I theta and r greater than 0 minus pi less than theta less than pi. So if I'm going from this point to this point, indeed my theta will always lie between minus pi and plus pi. So there is no issue there, and so we are not crossing any branch cut if we're using this. And therefore, we can go ahead and evaluate this. It's continuous at all points, and then your resulting antiderivative itself does not ever cross any branch cut, right? And therefore, you simply get log of Ri minus log of minus Ri, which you can evaluate to be log r plus I pi by 2 minus log r minus I pi by 2, corresponding to the final angle and the initial angle. And if you calculate this carefully, you just get I pi, right? However, if you evaluate the second of these integrals over C2, then the principal branch would be unsuitable, because if you take the principal branch, then there is a branch cut along the negative axis, and which you should not cross. So as far as this integral over C2 is concerned, we should consider a different branch. So let's take this branch, take a branch in which the branch cut is along the positive axis. In other words, I allow theta to run from 0 to 2 pi. If I do this, then I can go ahead and use this result, which is that I take log of minus Ri minus log of Ri. So the final value minus the initial value, and so in this case it will just turn out to be log of R plus I 3 pi by 2 minus log of R plus I pi by 2, which is I pi. So I can just stitch these two together, and then I get I pi plus I pi, which is 2 pi I. So in fact, the contour integral of the function 1 over z dz for a contour of this kind, which goes around in some closed contour around the origin, is not 0 but actually 1 over 2 pi I, and it's 2 pi I, right? So this is a result of very great importance, and we will return to it later on, right? And it has very important consequences, and so this is the first time we are explicitly stating this. You can also work this out by other methods, right? So but I thought that it's useful to point out that when we are working with antiderivatives, it's important to be careful, right? Although this function 1 over z itself is not multi-valued, so in some sense at any point you're going along this contour, it's completely well defined, you're not doing anything illegal. But the thing is that if you want to directly use this result, which is this path independence of a contour integral, that can happen only if your antiderivative itself is meaningfully well defined at all points along this this contour, and you don't cross any branch cuts, right? So that's why if you take a different branch and evaluate these two bits of your contour, then it's a legitimate calculation, and then you get 2 pi I, which is also a result which you can obtained directly from other methods. Okay, so in this lecture we have seen the idea of an antiderivative and how with some care we can use this notion to evaluate certain contour integrals. Thank you.